So I'm Greg Corrado from Google.
Thanks.
Vince started by saying that he was a real computer scientist, but not a real expert in AI. Well, I'm not sure I'm an expert in AI, but I'm definitely not a real computer scientist for having accidentally gotten my PhD in the wrong discipline. Clerical error. This is the last talk of our morning session about the frontiers in machine learning. And my purpose here is to try to summarize and distill the ideas that we've heard in the morning so that we're entering the afternoon sessions kind of with a common understanding of what really is achievable and what the potential implications are. I also recognize that I'm the last thing standing between you and lunch, so I'll try to do this as briefly as possible. So I think the first thing that we really want to understand is that machine learning really already is everywhere. It's not just wonderful work in academic labs. It's in products that huge swaths of the population already use. It's both doing things like making familiar and existing products and services better, like making Google search more accurate by using a deep learning system to understand long natural language queries, but also by creating entirely new things that aren't really plausible or tractable without machine learning. So for example, an automated email reply service is something that you're just not going to consider without a machine learning approach. To review, I think we all kind of are getting our minds around how these different fields are related to each other, and artificial intelligence, right? The notion of trying to make machines intelligent is both much larger and more general than machine learning, which is really about making machines that learn. But whereas these traditional AI-based systems were more engineered, it was more like they were programmed to be clever. A lot of the advances that we've seen in the last 5 and 10 years have been about trying to make systems that are both intelligent and learned. But there are really occupants of all the sectors of this Venn diagram, right? You know, IBM Deep Blue was an exquisitely well-engineered chess engine that used some of the techniques that Vint talked about to search for the space of possible board configurations. It was certainly artificial intelligence, but it didn't use machine learning in almost any meaningful way, whereas AlphaGo, which beat the Lee Sedol at the game of Go, was almost entirely learned, even though we're still talking about board games. And I just do want to point out that there are examples of machine learning that almost no one considers intelligent. So ATMs have been reading handwritten checks using machine learning since the late 90s. But I don't know about you, I've never had the experience that I'm interacting with a profound intelligence when using an ATM. It's also important to understand that I think for the larger community and the people that we're communicating with, that robotics, although it interacts with artificial intelligence and machine learning, is fundamentally different, right? It's about making machines that move. And although machine learning may be useful in trying to help machines move more fluidly, it is itself a separate discipline. And I think much of the global community doesn't actually quite get that yet. To give a really concrete example from practical product world, about classical AI versus ML-powered AI, we can only use email because our inboxes are defended by spam filters. There's far more spam in the world than there is real email, and that's not even counting the things that you get on lists, right? And whereas the classical AI approach really was based on rules or contingencies to try to identify what things were candidates for being marked spam, all the modern systems use machine learning in some way or another, where now a computer program basically looks at some historical log of messages and how they were marked as spam or not spam, and then tries to change itself in order to become more accurate at that. And that's really the funny bit that is sounds magical when you first hear it. Oh, change myself to make fewer errors. If I could do that every morning, that would be really great. But it sounds far more magical than it is. And not to belabor the point, but I'm just gonna go through really quickly, how all of these things are actually working is just, it's so dumb, it's almost comical. Yeah, it's the road to building intelligence is paved by dumb stones. So machine learning systems, almost all the practical ones are in this framework where we have crisply defined inputs and outputs. So as a simple example, let's imagine we're just trying to do some simple statistical estimation problem, like estimate what a student's grade would be based on how many hours that they've studied. We have some notion that there's going to be a relationship between these two things. Oh, maybe, the more you study, the better it is. Maybe the test is really easy and you don't have to study very much. Maybe the test is actually not a very good test and it's a very shallow relationship. But machines don't even, in most cases, we don't build practical machine learning systems that have valid priors. And most practical machine learning systems start out in the world equally likely to draw this nonsense curve or this even more nonsensical curve. And how does the machine even know what relationship, what hypothesis it's entertaining? There's always some form of mathematical equation. This all comes down to some way of representing a relationship, in this case parameterized by just a couple of numbers. And if the machine wants to draw a different line, wants to entertain a different hypothesis, anthropomorphizing egregiously, it just changes the values of those two numbers. So this is, this basic idea that most of machine learning is function estimation, practical machine learning is mostly function estimating, or line fitting is not too strong a thing to say, I don't think. And it's really broken down into this notion of, well, the engineers or the people who are building the system, they often describe what the general class is of things that we're considering. They define what the equations are at play, and the machine learning system is only really learning the parameters of those equations. So, we initialize the system, it's drawing some random line based on how we've initialized it. It sees a single data point, and then all that it does is it changes the parameters, those two numbers, in order to make the error smaller. This is critical. A lot of people don't understand. It doesn't make the error go away. It just makes it smaller. And as it observes more data, it just continues to make the line better and better and better. And this is kind of a really lame way to fit a line. We all know that there are better ways of doing this in practice. But this is what the common algorithm that we all use, stochastic gradient descent, would really do if it were trained on these single examples. But it's true that after it's seen a large amount of data, it gets a pretty good estimate of what those parameters should be. And so machine learning by example, really does kind of break down into these boxes where, you have some people that are thinking about what is the model, what is the equation. Some people are thinking about how we should represent the parameters. And then there's this whole world of algorithms where we try to figure out, well, what is the best way of comparing the predictions of this system to what we actually observed in order to change the parts of the model that we have blessed as changeable by being the parameters. And then it's easy to make predictions. You can just plug in new values. And indeed, this is actually usually why we're building the system, is because we want to run predictions forward. So now we can say, oh, well, my estimate for how well a student will do is 91 points if they study 3.5 hours. So this is actually a very general framework, but it's really, really gradual. The fact of the matter is that the more complicated you make the systems, the more slowly they need to make their changes in order to do well. And I think that this is the answer for why this is happening now, right? Why have we been waiting for machine learning? We get to ask this question all the time. And to me, it's just like an analogy to the human quest for flight. In the 1890s, there were plenty of people around the world trying to build flying machines, and they were all stuck to the ground, and they didn't know why. And that's because they were all using boat anchors as engines, right? The power-to-mass ratio of the internal combustion engine was simply insufficient for powered flight in the 1890s. The people then didn't know that, but that's exactly what was going on. Fast forward 10 or 20 years, and flight becomes quite tractable. And indeed, the first people to fly were people who built their own internal combustion engines to be as light as possible for the 90 seconds we were going to be in the air. I imagine they had to rebuild it after every flight. And that's exactly what's happened in machine learning as well, is that people had been trying to do this for a long time and truly didn't realize that what was holding us back was computational power. And now, through the natural progression of computational power in CPUs, through the progression of Moore's law, that's going well. A lot of deep learning research was actually catalyzed by the realization that we could use graphics processing units and repurpose them for computation. And as Vint already mentioned, at Google, we make some custom silicon to make it run a little bit better. So even though this is general, it is quite slow. But this learning by example version that I'm touting here, right? We recognize this as in the jargon of the field. This is supervised learning, right? Trying to take examples of correct behavior and distilling that down into a system that's able to reproduce that behavior moving forward. And this is amazingly effective if you have a large number of examples to learn from. But there are other kinds of machine learning that we've mentioned before, like discovering patterns and unsupervised learning. Data clustering, which is mentioned, is a great example of that. There's also reinforcement learning, which I think is growing in popularity again and may have some influence on the future. And indeed, AlphaGo used some reinforcement learning. But if you look at what is actually happening today and what is working and powering real products, it's almost all supervised learning. It's all about getting some examples and then getting a machine that is able to ape and then generalize from those examples. I think every speaker who's been here has so far has mentioned deep learning. So let's cover what deep learning is. As Zubin said, it's really just the model part. Right? You can mix and match what goes on in these other boxes, right? It's just about how you get from the input data into the output, what the prediction you're trying to make. You're not going to go from a photo of a cat to the text string cat using the equation for a line. Instead, you need a much more complicated formalism, and that's where the deep neural network comes from. The term deep, just a reminder, is that if you when I was in grad school, if you went to a machine learning conference, everybody was trying to get from input to output in 1, 2, or 3 mathematical operations, right? And actually, almost everybody was at 2. You would have one mathematical operator that extracted some features, and then you had something that like an SVM or something that then went from those features to your final prediction. And deep learning is really just the realization that it is tractable to break a problem down into 10, 20, 50, or 150 tiny steps rather than trying to make 3 giant leaps. So it's a class of machine learning models. It's just artificial neural networks from the 1980s all over again. And it's compatible with all of the variants of machine learning. Although it's mostly used with supervised learning, it's certainly compatible with other approaches as well. So the mistaken PhD that I got was in neuroscience, which was me spending 8 years finding out how little we knew about the brain. So we don't know very much. And deep learning is only based on a small fraction of what little we do know, right? And this is something that is sometimes overhyped. But the commonalities between artificial neural networks and real biological neural networks are really quite limited. It's really just the idea that we can build a very complicated system from individual components, each of which is mathematically rather limited, right? So your brain is made up of billions of individual cells called neurons. Each individual neuron is not particularly clever, but they can learn to coordinate, and the coordinated action of millions or billions of these is how we build bridges and write poems and things like that. And all that we're doing here is we're replacing those tiny little not so clever neurons with tiny little not so clever mathematical equations. And they really look a lot like y equals wx plus b, right? It's the engineer's version of the simplest computational function you can put down. And then what we do is we mash millions or billions of them together, and then we say, okay, you guys are going to learn to work together. Just the same way that the genetic code does not specify the role of individual neurons, but instead just lays out their rough topology, and they need to learn what the details of their communication. These mathematical functions, we as engineers, we just lay out their rough topology, and then they have to learn what settings of their individual local connectivities will allow them to accomplish their ultimate goal. And that's how we're able to do these amazing tasks that we've seen this morning, where you can now recognize objects and images and even have a conversation about an image. with a machine. And that is largely being implemented by these stacked decision makers, each individual decision maker not very clever. Of course, you know, these nice cartoon diagrams are belie the complexity of these things. The internal systems really are quite complicated, and I would say probably 60% of the people that are at these conferences are just putting out, you know, new, more complicated architectures and competing on, you know, how I can tweak the model or tweak the optimization approach in order to eke out slightly more performance. So like this, for example, is one of the architectures that we published and we actually used for real practical purposes. And, you know, as you can see, it's many, many layers deep, and the connectivity is not quite the simple serial thing that you might have imagined. But this works for real, right? It's not just something that you can do in a lab and you can't put in front of real customers. You know, it had been on my to-do list for the weekend to organize my photos for, I don't know, roughly 8 years, that, oh yes, I should organize my photos this weekend. And I never did that, and now I never have to, because we can all build computer vision systems that are able to recognize objects and images, and I can just search for, you know, dog. I can even search for terrier, right, and get that picture of a terrier that I know that I took. So it actually works quite well. I would say surprisingly well, given where we were just 5 or 10 years ago. But I think it's really important to understand that, this deep learning thing, it is not one function. It is a set of modular composable subfunctions. It's a Lego set for building models. And this is the point that was made earlier about the idea of differentiable programming. That what we've kind of moved into is now we have these individual building blocks that are differentiable. And we know that no matter how you stack them up, you'll end up with a complete model that is differentiable and then can be trained, can learn through this dumb method of make your errors smaller. As long as you can compute the derivative of the whole system, you can say, well, you got that wrong. I'd like you to make it epsilon better by changing your parameters by delta. But with the right choice of pieces, this deep learning stuff is actually really general. It's not one size fits all. You compose the pieces in a different way to solve each of these problems, but you can use it to recognize objects and images. You can use it for speech recognition. Every major speech recognition system, regardless of whether it's Google or Apple or Microsoft, is now using deep neural networks to do this kind of stuff. You can do it for translation, and indeed, that's how you get these amazing kind of captioning results that we just saw in the last talk. Now, within Google, this has really gone crazy as a way to make real practical services better. So we started our deep learning team in 2011, and it didn't work at all for the first year. And then after a while, it started working, and we've seen this very rapid adoption of people trying out using these machine learning approaches to make their product or service better. I don't know what these 3,000 people that checked in code to do this, but they've all learned to use these tools to try to solve their own problem in these specific areas. So let me give you just a sampling of some of these things which I do happen to be familiar with, right? So that spam example that I started with, that is a very real example. We had a system that had no machine learning, and then we had a system that had some machine learning for a few years, but it was a 2-layer kind of deal. And then you know, now we have a deep neural network, and now we're intercepting 99.9% of spam. And this is actually a really exciting and difficult problem. You don't think about this, but this is actually a real adversarial problem, not a thought experiment adversary, right? There really is a non-stationary distribution of spam that is changing to try to poison your inbox, and the system has to learn to cope with that. This is how things really work for photo recognition. Again, the model is a neural network, but it's a different neural network. Speech recognition, again, a neural network, a very different kind of neural network. And the neural networks are actually different enough that, like, the people that are at the conferences don't necessarily understand everything about each other's networks. But, you know, when this came out, it was the biggest single improvement that speech recognition had seen in almost a decade. Machine translation, similar kind of story, right? You can actually learn, these things can learn to translate in an end-to-end fashion. As Vint mentioned, we've gone from phrase-based to whole sentences at a time. And I want to dive into this one a little bit more deeply because I think that it's really cool and it's kind of an unusual example. It stands in contrast to the way that we do image processing, where we just dump the whole image in and then an answer spits out the top. The way that the machine translation system actually works is that it consumes the input sentence, the sentence in the original language, one word at a time. It's actually parts of words, but one word at a time, and develops a rolling internal representation of what the content was in that original sentence. And then only after it has consumed the entirety of the original sentence does it begin to compose what the translation is. And the composed translation is synthesized one word at a time, right? And is conditional on what it has written so far. And so you can actually draw samples from this where you have some probability distribution over what the first word is, and the system will choose different second words based on which first word is sampled. And this was a big improvement for us. So the yellow line at the top is how the quality of a human translation as judged by another human. They didn't know they were grading another human's translation, but they said, 6 out of 6 would be perfect. The yellow line is where self-identified bilingual translations are graded by other humans, and you can see that our old phrase-based system in blue was, meh, and the neural translation is much better. It's still not at the level of no. Do you remember when only Windows did this? And then Apple just, I don't know. I'm in Google whatever. Yeah. Anyway, the comical really. Anyway, we got a lot better. It's still not at the level that a bilingual human translates at, but for some language pairs, it's getting quite close. Okay, Smart Reply, this funny thing that I started with at the top where we're going to automatically respond to emails for you. In April of 2009, Google put out an April Fool's Day joke where we fake product announced, that Gmail was going to start replying to people's emails for you. Because obviously that's impossible in 2009. But 6 years later, it's launched to the whole world, for English at least, right? And then 6 months after the launch, it's accounting for 10% of all replies on mobile inbox. And that's not and I don't think that number is going to grow appreciably. It's actually just that 10% of the emails that you receive don't require more than a canned one-sentence response. And what the machine learning system is able to do is give you the kind of canned one-sentence responses that you actually need. Sometimes it impresses people. Like, I was having a conversation with someone in the legal department, and someone asked them, I really need this. This is really important. And the suggested reply was, I'll get it to you by the afternoon. And he was like, how did it know that was what I was going to say? We also had a case of a reporter who was had gone through a breakup and got an email from his ex-girlfriend, and the suggestion was, I just miss you so much. And he was mystified that it had feeling, and it was actually just, well, no, you're not the first person to break up over email. And the way that this system kind of works is again as a composition of machine learning systems. So there was one system that is kind of like a regular classifier that's just trying to figure out, is this the kind of thing that plausibly has a one-sentence reply? And then if there is a plausible one-sentence reply, we engage this other system that tries to compose one. And this is one where I get invited to join my brother for early Thanksgiving, and it says, count us in, we'll be there. Sorry, we won't be able to make it. But the thing is that this is actually very similar to the translation case, where what it does is it reads the incoming email one word at a time, comes up with basically a summary representation that is machine understandable but not human understandable, and then composes a response one word at a time. And this is this is related to how you build these kinds of captioning systems. But now instead of welding together a machine learning system for reading with a machine learning system for writing, you're welding together a machine learning system for seeing with one with writing. And the fact that these things are composable and jointly differentiable makes it easy to do all kinds of crazy things. Like, it did not take very many engineers to put together our text recognition system with our translation system, hack on some graphics at the end, and you get an augmented reality application that seems like magic. This is a silly example. You can also do other surprising things, like it was totally unexpected that you can take these artificial neural networks and feed them back on each other and they hallucinate. After you know that this is the case, you're like, oh, well, that's mathematically trivial. Well, that's true, but it's also cool. So it looks really good, makes pretty pictures, and there was an art auction in San Francisco, I think last year, of basically artists taking this tool and causing it to hallucinate fascinating things. This is, of course, how the AlphaGo won the game of Go, by being able to see shapes, right? But to understand whether a particular shape, even though it was a shape it had never seen before, did it seem like a strong shape? An application that we recently announced is, I think there are great applications of this in healthcare. So diabetic retinopathy is the world's largest and fastest growing cause of preventable blindness. If you know that you have this, there are some eye drops that you can put in your eye that will prevent you from going blind. But if you don't know that you have it, you'll lose sight. And indeed, I think it's 45% of people with this condition in India lose some of their sight before they realize they even have it. And that's because there aren't enough doctors to look at pictures of the back of your retina and decide whether you need to be seen by a real doctor. And the differences are, they're subtle, but they're not terrible. You could learn to do it okay for screening in an afternoon, right? And so this is exactly the kind of thing that I think that a machine learning system can do. And so we published this paper in the Journal of the American Medical Association earlier this year, where what we did was we had real professional ophthalmologists grade images based on whether or not they would want to screen them. We trained a machine learning system, just the kind that you would expect, nothing fancy, in order to process these images. And we can show that the system is as good as the doctors that gave labels to it. So this is a precision recall curve, sensitivity specificity, and you can see that some of the doctors are slightly above the curve, some of them are slightly below, but basically you're hugging the unit area line. Okay, so the last thing that I want to say is that I think that making ML work is tends to require 4 ingredients, right? We know that we need examples to learn from. Computational resources were the thing that was holding us back for a while. Creativity and ingenuity, I think, is actually the rate limiting step today. But the last thing is just having tools and algorithms. And this was already mentioned before, that it's really important to have tools that lower the barrier to entry. We've open sourced the software package that we use for all of our own machine learning systems. It's called TensorFlow. People can use it for whatever they want. And we only released it last year, and it's already the most popular machine learning repository in GitHub. It actually has more stars than Linux now, which is kind of funny. And part of the point of what we do is not just give away the tool, but try to teach people how to use it, because most of the engineers at Google, they went to school when machine learning wasn't cool, and now they all have to learn to use it, and they're doing so quite well, as evidenced by that exponential growth. I also think that it's really important to try to distribute this tech as globally as possible. So I think that's both by sharing the tools, right? By making the software tools readily available. There are many open source packages, making computing readily available through cloud computing. You can run these things on anybody's cloud. But I think that it's also really critical as a community that we share the knowledge, that there aren't walled gardens of innovation that prevent us from having an open dialogue about it. So open research publications are really important. Direct funding of community education is also really important. I think the open research publications is something that I'm really proud of that's going on in the machine learning community, where regardless of whether you're at academic institutions or whether you're in these companies, you're sharing the research that you've done. And just in the last 4 years, we've published a whole bunch of papers over 90 papers on just deep learning alone. But I do want to call out a couple of ones that I think will be relevant for our afternoon conversation, which is that you actually can do real hard-nosed engineering research on problems that are relevant to society. So we had one paper in the summer last year actually trying to formulate, well, what are the concrete problems in AI safety that we think could exist in 10 or 15 years, and how do we study them? And there was also a paper a little later on looking at what are definitions of equality and fairness in machine learning that we can actually directly deal with. So that, for example, this gave the example that was running example that was used here is, let's imagine something is giving a creditworthiness score, and we're going to decide who to give loans to based on a threshold. How do we analyze that system to identify whether there is bias in the system? And then how do we correct that bias without having to throw away the entire machine learning system? Because sometimes that's going to be intractable. And it turns out this is possible. You just have to think through it. So the final takeaways, hopefully in summary for our entire morning together, is that we now all understand the differentiation between AI, ML, and robotics, right? AI is things that are smart, machines that are smart, machines that learn, and machines that move, right? Those are the three subfields. Machine learning powered AI is already readily available and is all around us. It's definitely not magic, right? It's just a new engineering approach. And I think that it's really about just having the taste as an engineer of coming to a problem and being like, oh, wait, maybe I could just learn to do this part. Machines learn best from examples. I mean, I think that it's good that we're doing research in being able to use data in other ways, but the practical thing today is that they learn from examples. Data, software tools, and compute power are all important to making this work, but all three of those are now commodities. Those are things that are available to anyone. It's really human creativity that's the current rate limiting factor in what kind of innovation comes out of machine learning. Deep learning is the current growth tech. Everybody's talking about it. But as Zubin said, it is not the end-all be-all of AI, right? It is just one part. It's the thing that's working. It's very fashionable. People are flocking to it. But there are other things, and they will come to the fore. I'm a Bayesian, but I do deep learning all day. Why is this happening now? Just because computers are finally fast enough. There were some algorithmic advances, but they were tiny compared to the computers are finally fast enough factor. There are challenges. I think that there are important social challenges for us to think about in how we deal with this technology. But it's important for us to face these things together and as an open research community. And that's it.